scientists have made a groundbreaking discovery. They found a massive underground reservoir of liquid water on Mars. This reservoir is so large that it could cover the entire planet with water up to a depth of 1 to 2 kilometers or about a mile. This discovery has solved a long-standing mystery about Mars. What happened to all the water? Mars wasn't always the dry, dusty planet it is today. Billions of years ago, Mars was a very different place. It had a thicker atmosphere and a warmer climate, allowing liquid water to flow across its surface. How do we know? Well, 3 critical pieces of evidence show water once flowed on the red planet. The first is a network of valleys and outflow channels. Mars is dotted with features closely resembling river valleys and deltas on Earth. These networks are branching. The second is the presence of hydrated minerals. The detection of minerals that only form in the presence of water, such as clays, sulfites, and certain types of salt, provides strong evidence that water once existed on our neighboring planet. These minerals have been found by orbiters like the Mars Reconnaissance Orbiter and by rovers like Curiosity. Finally, Martian rovers have discovered sedimentary rock formations on the planet, similar to those formed by water processes on Earth. These layered rocks often show features like cross-bedding, which occurs when water flows over a surface, and ripple marks created by moving water. But between 3 to 4 billion years ago, Mars experienced a series of catastrophic events that dramatically altered its history. The trouble began with the collapse of its magnetic field. Unlike Earth, Mars lost its global magnetic field relatively early in its history. This magnetic field, created by a dynamo effect within the planet's molten core, would have shielded the Martian atmosphere from the solar wind, a constant stream of charged particles emitted by the Sun. As Mars' core gradually cooled, the dynamo effect weakened, leading to the eventual loss of the magnetic field. With the magnetic field gone, Mars' atmosphere was left vulnerable to the persistent solar wind. Over time, this solar wind stripped away much of the atmosphere, causing the atmospheric pressure to drop significantly. As the atmosphere thinned, it became increasingly difficult for liquid water to exist on the surface. Water that might have once been present in liquid form began to evaporate and escape into space. The thinning atmosphere also led to a weakened greenhouse effect, resulting in a sharp drop in temperature. Mars transitioned from a warm and wet environment to the cold, dry world we see today. As the planet cooled, any remaining liquid water froze, becoming surface ice or permafrost hidden beneath the surface. But something didn't add up. If our theories were correct, even after accounting for the water lost to space, Mars should still have a significant amount of water. The frozen water in the polar ice caps wasn't nearly enough to account for it all. This raised the intriguing question, where is the rest of the water hiding on Mars? And if it still exists, could it potentially support life as we know it? The answer came from NASA's InSight lander, a groundbreaking mission that aimed to explore Mars' interior structure. Unlike previous missions, Mars' interior structure was not exactly the same. Unlike previous missions focused on surface exploration, InSight was designed to dig deeper, literally and figuratively. Its mission was to investigate Mars' seismic activity, heat flow, and internal composition by looking beneath the crust. Throughout its 4-year mission, InSight detected more than 1,300 Mars quakes. These quakes originated from meteor impacts and rumblings from volcanic areas, all of which produced seismic waves, which caused the Earth to collapse. Was a surprising discovery, a large reservoir of liquid water. The technique used to make this discovery is similar to what scientists use on Earth to study our planet's internal structure. By analyzing how seismic waves behave as they travel through different materials, seismologists can infer the properties of those materials. To locate this hidden Martian water, scientists applied a mathematical model of rock physics similar to those used on Earth to map underground aquifers and oil fields. The model revealed that the seismic data was best explained if, deep below the surface of Mars, there existed a layer of fractured igneous rock with its cracks filled with liquid water. Igneous rocks are formed from the cooling and solidification of molten rock material, either magma below the Earth's surface or lava on the Earth's surface. This process occurs in various ways, such as beneath volcanoes or as lava flows after volcanic eruptions. As igneous rocks cool and solidify, they can develop fractures and cracks. These fractures can create pathways for water to flow through the rock and be stored in the spaces between the cracks. Over time, these cracks can widen due to processes like weathering, allowing even more water to seep in. Though igneous rocks are not typically the most porous or water-resistant, retaining type, they can still hold water under certain conditions. While the discovery is essential in our understanding of Mars' water cycle, this layer is buried at depths between 11.5 and 20 kilometers, or 7 to 13 miles, making it far too deep for future astronauts or current technology to reach. Even on Earth, drilling to such depths would be an extraordinary challenge. Although the existence of liquid water on Mars doesn't automatically mean that life exists there, it certainly opens up intriguing possibilities. The conditions within this underground reservoir could be similar to environments on Earth where microbial life thrives, such as in deep mines or on the ocean floor.